All right. What is going on? All right, sorry about that, guys. So this is my now second time doing this because I accidentally did the whole a lot of the recording muted. So this is worksheet 5. This week we're going to be doing 2 worksheets, that being worksheet 5 and worksheet 6. So stay tuned for that. I'm going to be doing that during the next SI session, and then Friday will maintain itself as a Q&A. Other than that, please sign in, and I'm just going to dive into it because I don't want to. I have other students here right now, and I don't want them to hear the same thing. But I'll make sure to go over the key things. So this is basically just me summarizing the difference between the magnetic field and magnetic flux. I encourage you to pause it and just read these definitions. I think that it'll really clear it up. I think that the most important thing for you to remember is just the magnetic field describes a region where the magnetic force can be felt. And differently, the magnetic flux is how much magnetic field that passes through a closed like unit area. So we'll see both of these instances applied shortly. This slide is just full of definitions. I think that they're all better seen in an example, but I just want you guys to remember when you see magnetic field lines present, an EMF will be induced as long as current is not constant. And then when you see this coil moving into a magnetic field, we got to use a different formula, that being, the BLV one. And with Faraday's law, you can put an absolute value on the EMF and solve like that, but just don't forget that minus sign per Lenz's law. DC versus AC. DC we're all very comfortable with now. It's just the current will always be in one direction, and then AC, it can fluctuate directions with the changing magnetic field. Here are our formulas. It's just, this is going to be the field times the unit area times the angle between them. Oftentimes these two will be perpendicular, B and A will be perpendicular to each other. And then this is just, this is that special instance right here where it's a loop in the magnetic field. Other than that, inductance, it's not a formula we will probably use that much, but just in case you need it in your back pocket. And then for LRC circuits, these is a question I'm pretty sure would probably be on midterm 2. It's just like, a formula plug and chug party day. It's just a lot of memorizing these, or not memorizing, I bet you they're given. It's just applying these formulas. So pause if you need to, copy these guys down, and I'm just going to dive right into the content. So let's just move it on. We have this rectangular loop being pushed to the right where the magnetic field points inward. Therefore, we have a magnetic flux increasing into the page. Okay, so we have this loop. It's getting more, its area is getting more into the region where there's a field going into the page. So therefore, its flux is increasing into the page. And that's, so that's because the area of the loop is increasing into that range. So we want to oppose this by Lenz's law. So how do we oppose that? We're going to need more magnetic field going out of the page. So right now we're increasing in. To oppose that, we need more going out. To get this field, an induced current would need to be produced counterclockwise. Okay. And then here's just our curl right-hand rule. Thumb the direction the current is flowing, and then your fingers will curl in the direction of the magnetic field. Okay, so here's just multiple examples of all of that. So we can see in this case, let's just look at this one. So right now we have arrows, it's going from the north outwards. So an arrow is starting where my mouse is right now, start right here, and it goes out this way. So right now we're having more in. So how do we, react with that? We need to have more. So we have more in, we need to have more out. So that tells us it will always be counterclockwise, right? So if you imagine there's an axis going right through this middle right here, we rotate it towards us. So we're looking straight down towards it. We'll see that that's counterclockwise, right? So what you should kind of make from this chart, and feel free if you want to make it and send it to me, I'll verify it as correct or incorrect. Like the situations when you have, more going out or more going in, and the effect on the induced current. So if you want to make a chart, you're saying like, more going in. To oppose that, we need more out by Lenz's law. Therefore, the induced current will always be counterclockwise. So if you guys want to do like all 4 of those scenarios and send it to me, I'll be happy to double check that, or you can just like, find it online or whatever. But yeah, so I think the best way to challenge these guys is to just view them as they would be asked. So in the first one, current's constant, so no induced current. This is kind of a rule of thumb. Keep that in your back pocket. It might come up. Other than that, I realize also the arrows are unclear, so I'll try to just let you guys know which way they're pointing. So right now in this one, we have a current that's decreasing, pointing downwards. So we put our fingers on that line. We curl our fingers in the direction the field will be going. And we'll see that, I apologize, I feel like I recall that the Zoom is flipped. So you just have to like hear my words and follow. You put your thumb on the direction the current's going. So like right now I have like a thumbs down sign. I'm holding the page straight up. I'm doing a thumbs down sign. So thumbs down in the direction it's pointing. My fingers curl towards the circle, and where they hit the circle, it tells me which way the field is pointing. So right now my fingers curl in. Because I is decreasing, we know B is decreasing in. So how do we oppose a decreasing in? We need to increase B in. Therefore, it will all be clockwise. So decreasing in, we need to increase in. So therefore, we need a clockwise induced current. So that little phrase I just said, that little like proof kind of, that's the kind of thing you would want to write down for like the 1 of 4. Decreasing B in, increase B in. So decreasing B in, that's what you have, what you want to do, increase B in, and that will always have a clockwise induced current. So again, I'm going to do the thumb thing. Thumbs pointing down, fingers curl towards the circle, and that's why I know B is going in, because my fingers are going into the page. All right, C. So here we have, again, a current decreasing. This time it's pointing eastward or to the right. So I'm going to line up my thumb. Sorry if you guys are watching, it's going to look weird. Line up my thumb, curl till I hit the circle, and I'll see now my fingers are pointing onto the page. So thumb lines up, curl till my fingers till I hit the circle. I have decreasing B out. What's the opposite of that decreasing B out? We need to increase B out. So what's the induced direction of current? That'll be counterclockwise. All right, last one. Thumb on the page, curl my fingers till I hit the circle. Again, my fingers are pointing out, counterclockwise induced. So where now we are increasing B out. What's the opposite of that? We increase B in, and there will always be a clockwise I induced based on that. All right, pause real quick and let me take some questions. All right, we're back. Okay, so here's that solenoid type question. So it's being pulled away from the loop. In what direction is the induced current? So we're going to be using the right hand rule, and we're going to be first looking at this part in purple right here, a little curl right there. So the right hand rule tells us that we have a field going from right to left, like that, and it is decreasing out of the loop towards the right. So like that, right? And then per that logic, we know it's going to be a counterclockwise induced current. So we need to use, first we need to establish it's going from right to left. I'm sorry, excuse me. It's going from left to right. And then the B field is going out towards the right, out of the loop towards. So what do we need to do if it's going more out? We need to have, wait, I just can't do myself, one second. Okay, yeah. So right hand rule tells us it's moving from left to right. The B field is decreasing out of the loop towards the right. So therefore we need to have an induced current that's going to be going counterclockwise. Okay, that makes sense. And again, if you rotate it towards you, so you're looking straight down at it, you'll see kind of why that makes a little bit more sense. I think it's just hard with all the loops that are going on. So we have a north pole of a magnet is being inserted into the coil. In which direction does the induced current flow through the resistor R? So that means it needs to be specific to this area. So obviously, that field's coming out in that end, that north pole. We have our current flowing through like this, And I just recommend that you just choose one loop and focus on it there. We'll know that the B field is increasing from left to right as it's getting closer. So we want to oppose this. So therefore it must be going right to left or clockwise. If you're looking right here, clockwise here, but from here it's going from right to left through the resistor. Okay, so I think that these are just more difficult for you to visualize. I suggest like when you work in it with it in a problem, you'll kind of see why these things hold true. And if not, you should look up the Khan Academy video. They have a very good like 3D like rendering of it, and it makes it easier to see. I think it's like versus me who's mirrored on Zoom trying to show you my hands. Okay. So let's just take a look at this first question. It's just a lot of question, but it's actually very quick, as you can see here. So what we're looking at here is a part of a rectangular loop with a wire with the shown dimensions inside of a region with uniform magnetic field. Total resistance to the loop is given. The loop moves at a constant velocity to the right. So the first thing is we're going to look for the initial induced current, magnitude, and direction. So right off the bat, we can see that we're dealing with a loop that's moving through a field. So we know to use that EMF BLV equation. That's like kind of our special case. So just keep that in your back pocket. And then at this point, we can just plug in everything. They gave us the field, they gave us the length that's in that loop, and they gave us how fast it's going. And you can just solve for that 0.6 volts. Next thing we're going to do is treat it like a, as if we're using V equals IR, except we're just, solving for that I, and we just solve for I. And then how do we know which direction it goes? So there's a few ways to think about it. The first thing is between these 2 points, you know that there will be a separation of, the plus and the minuses. So there's almost like a fake battery acting right here. Like a bunch of minuses accumulate down here and a bunch of pluses accumulate up here. So this is like a DC current in that regard. We'll see that there's a current that's going to be flowing clockwise. But I think kind of more powerful than that is right now we have this loop moving out. So what's the opposite? We want to have more going in. Wait, we're moving out. Okay, so it's moving out, so that means we have less in. So what do we want to do? We want to put more in, so that holds true. By definition of more in, that tells us we're going to be having a clockwise induced current. And then, like I said, if you're going to kind of visualize it like the DC, that fake battery that's going to be acting here kind of confirms that direction of current. All right, so now we've established why that's clockwise. For the remainder, you're just going to have to use these equations that we've become kind of comfortable with, just to solve for, like here we're looking for power, and here's that force, and it's acting leftward. Leftward, you might ask, is a kind of confusing one, but how do we know that? And that's because, the forces that are acting straight up here and down here will end up canceling because they both have that shared unit length, and they're just pointing in opposite directions. So what we're left with is just the one purely pointing to the left. And then in part D, we're asked how its velocity is. It's actually decreasing because we're using the right-hand rule. We can see that there's a force to the left. And that's just, we like line up our hand with the, or I don't know how you guys use your right-hand rule, but for me, how should I explain this? So you're gonna line and let's talk about right here. Which way is the force pointing? Straight up, right? We line it up. We have the force, we have the field going in and our thumbs pointing up. Down here, the opposite, it's pointing down, and here it's pointing to the left. So with only the force existing on the left, it'll be kind of opposing this guy right here. So it'll be decreasing its velocity and its ability to like escape this zone. Okay, and then in part E, it's asking us about the current of the circuit. And again, it will decrease as V decreases. And then we're going to calculate the force required to pull the loop from the field. And it's just going to be just enough to oppose the magnetic flux because, constant velocity, net force equals 0. The only way to cancel out this F is with, equal and opposite, just of different direction. Okay. I'm just going to move on to, which time do we have? Oh, good. Number 2 here. Actually, let me pause real quick, ask questions. All right, so I just answered a few questions, but another point of emphasis is just like recognizing this is going to be a clockwise induced current, just because as you know we slide it to the right, we're going to have less of this area, and we're going to have a decrease of B in. So how do we oppose that? We need to have more B in to make up for the less B in, and that will tell us we're going to have a clockwise induced current. And that kind of leads us to our direction of forces, right? Like use our, I forget what he calls, like the 3-finger right-hand rule. And you can see like at the top here, the force is going to point up. At the bottom, it's going to point down. And here it's going to point to the left. And that's because our current's kind of going, it's going this way. So it's got to line up. And then we'll know that the force here cancels the one that's going down this way. Cool, cool. Okay, so now we're looking at question number 2. And it's just an LR circuit. So we're given an EMF. We can kind of treat that like our battery voltage drop. We're given the resistor and the inductor. And then we're giving at a certain time a current of 3 amps is going through its resistor. So the first thing is we're looking for a potential difference across the inductor at this time. Potential difference that refers to a change in V. So we first need to test if it's increasing or decreasing. So to do that, we're going to start with I max, and it's a similar situation. We do V equals IR. I rearrange to solve for I, and I call it I max. At this point, I solve for the maximum value the current can be. So what this tells me right here, I just do this math right here, 5 amps. I have at a time of 3 amps, and at the max, it's 5 amps. Therefore, we know that the current is increasing. So this is a test. You don't even need to do this technically to solve the problem. Wait, let me scratch that. This is kind of a separate part of the question within the same question. You need to prove if it's increasing or decreasing to know how to set up this equation, right? So per the fact that it's increasing, we add this V2. Had it been decreasing, we would subtract. So at this point, we just got to solve. We got to plug in everything. We have our change in V. We use IR, and we're looking for that V2. We solve for V2, that equals 4 volts. Next, in part B, it wants to draw the negative sides of the inductor at this time. So as the current is increasing, the voltage drop occurs in the same direction, because from the plus to minus sign. So increasing top to bottom equals an induced current, right? So because the current is increasing, the voltage drop occurs in the same direction. So, plus to minus right here. Okay. And then part C, which direction is the induced current flowing through the inductor at this time? I induced increases bottom to top. So it acts in the opposite direction as that. And then is the current increasing or decreasing? And we kind of proved that in the beginning, it's increasing. Okay. So this one's just kind of a definition check. And let me take back what I said. I said it's not necessary to do this part, but that's not true. You actually do need to do this part to do everything else, but it is kind of a separate part to solve because it kind of guides how you're going to be treating each step. Okay, so I just have one more question, and this is kind of the one that is pretty commonly seen. So we have an LRC circuit with the components in series connected to an AC power supply. They gave us R, L, C, and then V naught, V. Excuse me, they give us V naught and then the frequency. So the first thing we're going to do is solve for Z. So here's our equation to solve for Z. At this moment, you can notice that we have that XL. It stands for, that tells us we're going to be solving for this guy, and the XC, that's going to be using this guy to solve. So they both have their own respective equations. This is probably on your formula sheet, but now we can solve for XL and XC. All right, you just work those all the way out, and then you have enough to plug into Z to find the Z value, 9.4 ohms. Okay, and you kind of treat this as like the resistance of everything, that it being the resistors and the inductors. Okay, next thing we're looking for is to find the peak current. So to do that, we're gonna have to use that V naught that they gave us. We just do some rearranging and then we just solve. Next thing, we're gonna look for the voltage across each circuit component. So here, these guys don't all add up, and that's just because it's the exact phrasing here. I haven't showed you when they do all add up. So for now, in this case, they do not all add up. So instead, you just have to solve each one. So it's all going to be using that current that we found previously. And then we're going to be plugging in that XC, XL, and R. Next thing we're going to look for is that phase angle. And that phase angle will always have this equation. We're just going to, sorry, there should be a inverse cosine here. And then we'll end up finding our theta. Okay. So that's that. Again, we're going to do worksheet 6 during our next session. I'll post the recording for that. So stay tuned. Email me any questions. Thanks, guys. I'm going to pause it. I'm going to end the recording here.